Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at sets. So a set in maths is just a collection of objects. We usually denote it with a capital number. So when we're writing the elements of a set, we use these squiggly brackets. So this says S is the set that contains 1, 2, 3, 4. Each of these is an element of S or a member of S. So we write something like this to mean 1 is a member of S. For example, 5 is not a member of S. So it's kind of like the same symbol just struck through. So S is a set with 4 elements, T is another set with 4 elements. So this symbol here means intersection or and. It's very similar to this operator we saw in logic. So S and T is the set that includes the elements that were in S, but also in T. So in this case, it's just 3 and 4. This is read S or T. This symbol U, which means union, is very similar to this symbol that we saw in logic. So S or T includes every element that is either in S or T or both. So it would be 1, 2, 3, 4, 5, 6. We don't write the 3 and the 4 twice, even though they occurred in both sets. So this notation here means the cardinality of S. For a finite set, it just means how many elements, how many members are there in the set. So of course that's 4 here. So this notation means the power set of S, and that includes all the subsets of S. So there are quite a few here. So let's look at subsets of S. So firstly, we're going to use this notation. This here is the empty set, the set with no elements. That is actually a subset of any set. So the other subsets of S, so we're going to include all the subsets that have only one element. Now we're going to include all the subsets of S that contain 2 elements. And there are 6 of those listed here. Note that we don't write 2, 3, and 3, 2 separately. They are the same subset. So now we're going to write all of the subsets of S that contain 3 elements. And finally, we need to include the whole set of S because any set is a subset of itself. So we can see the power set of X contains 16 elements. That's actually no coincidence. S contained 4 elements. It turns out if a set contains n elements, its power set contains 2 to the power of n elements. So the number of elements we expected to be here was 2 to the power of 4, which is 16. So the power set is a set whose members are themselves sets. In other words, every member of the power set is another set. And note that every set has the empty set and the whole set as a subset. All right, this is all well and good for finite sets, sets with a finite number of elements. Let's look at some infinite sets. So examples of infinite sets are rationals, integers, naturals. This means irrationals, real numbers, and this is the set of all numbers from 0 to 1. So the size of each of these sets is infinite, but people realized long ago there's sort of different types of infinity. So it turns out that all of these sets here are said to have the same cardinality. It's kind of like aleph naught is the way it's said. It's hard to draw the n there, but they all have this infinite number of elements. So these 3 sets have more elements. They're also infinite sets, but they're said to have like a higher level of infinite number of elements. So each of these is said to have cardinality aleph 1, which is actually just 2 to the power of aleph naught. These 3 sets are said to have the same number of elements as the power set of each of these. So it is a tricky concept to wrap around your head. How could the rationals and the integers have the same number of elements? I mean, clearly there would be more rationals than integers, right? So when we're talking about infinite sets, it might be helpful for you to not think of this as the number of elements, but just think of it as the cardinality of the set, a measure of the size of the set. So these 3 all have the same number of elements in the sense that they all have infinitely many members. There are infinitely many integers, just as there are infinitely many natural numbers. But they're sort of the same level of infinity. All of these sets has the smallest infinite number as their cardinality. Whereas we've seen before, there are clearly way more irrational numbers and real numbers than any of these. So these have a different cardinality. And the continuum hypothesis says there is no set that has a cardinality more than this, but less than this. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.